Professor J. McClelland studied psychology at Columbia and the University of Pennsylvania, where he was exposed to behaviorist approaches to understanding behavior, sensory neurophysiology, and the cognitive psychology of the 60s and early 70s, which was dominated by the computer metaphor and the idea that the brain was only of peripheral interest. Seeing limitations to this approach, he found himself trying to understand cognitive processes in terms of propagation of excitatory and inhibitory signals between neurons around the time he joined the faculty of UCSD in 1974, where he met David Rumelhart. Inspired in part by Rumelhart's interactive model of reading, Jay and Dave teamed up to develop the interactive activation model of letter and word perception. From there, he and Rumelhart went on to form the Parallel Distributed Processing, or PDP Research Group, publishing the 2-volume work Parallel Distributed Processing, applying neural networks to a wide range of cognitive and neural phenomena in 1986. Rumelhart and McClelland jointly received several awards, including the INNS Neural Network Pioneer Award for this work. And McClelland has received many other honors, including the election to the National Academy of Sciences. In 1984, McClelland joined the psychology department at Carnegie Mellon University, where he created the Center for the Neural Basis of Cognition, then moved to Stanford in 2006, where he founded the Center for Mind, Brain, and Computation, which he continues to direct. Well, that's quite a resume. But first, I'm David Brown, and I'm the chair of the College of Fellows of INNS, and we have a history project to record conversations with some of our great pioneers in AI. Well, Jay, how did you get into the field?
Well, I like to start with my kind of attempt to integrate what I learned in my undergraduate sensory mechanisms class with what I was learning as a cognitive psychology PhD student at the University of Pennsylvania in the early 1970s. When I took, sensory physiology for a man named Leonard Mayton at Columbia, he taught me about excitation and inhibition and simple neural circuits. And he taught us how to understand, the phenomenon of perceptual contrast in terms of simple excitatory and inhibitory interactions between neurons in the eye of the horseshoe crab. And, there was something about that resonated with the sort of Skinnerian approach that there's something about behavior that transcends all species. There's, we're all like these behaving organisms with nervous systems and stuff. Skinner didn't want us to look inside the black box, but he did want us to think about the general mechanisms. And so when I started studying cognitive psychology around 1970 as a first-year PhD student, I'm like, wait a minute, we're being asked to think that humans are unique and, that there are all these human abilities that aren't shared with other species, and that, sensory processes aren't really relevant to any of that. And I'm like, no. So I was also taking physiological psychology as a first-year PhD student, and the divide was incredible. Even though the professor of teaching my neurophysiology class was married to the professor of developmental psychology, they worked in different domains completely. And so I've always, wanted to integrate mind and brain, I think, and to think in terms of brain-like mechanisms that would implement things that we experience, like you put a field of gray in the middle of a background. If the background is white, this field looks dark. If the background is black, the field looks white. That's a very striking effect, and it occurs in the eye of the horseshoe crab as well as in the human mind. And so, very basic neural circuits can account for this kind of phenomenon. Okay, so I started wondering about how I could apply this to thinking about human cognition. And I had been studying the perception of letters in words. I've been studying how context facilitates perceiving a letter. So if a letter is embedded among other letters that it makes a word with, you see that letter better than if it occurs like by itself or in a jumbled arrangement of random letters. And trying to envision how this could occur. And I wanted to imagine that our knowledge about what letters looked like mediated our access to our knowledge about what letters went together to form words. But the only ways that anybody had of thinking about that around 1970 were that first you identified the letters. You had this discrete result, sequence of letter identities, and then you looked it up in the dictionary. Oh, is there a word W-O-R-K in the dictionary? But you already identified the letters. And I'm like, that couldn't explain my effect, right? Because you see the letter better when it occurs in the word. So if you had to see the letters first, and people would say, oh, look, this is an oxymoron. This can't possibly be a real effect because you have to see the letters before you can know what word it is. So I started looking for models in which, your sense of the identity of a letter was a matter of degree. And maybe the bottom-up input would say, oh, there's several letters possible here in terms of the visual features that I see. But then in other positions, you have other letters that are possible, and they might sort of excite and inhibit units for words that they were consistent with. And if you just imagine this continuous propagation of activation with partial activations, the letters that were consistent to form a word might activate one word more than any other, and then you'd know what word it was. And so I was thinking about that idea, came out of my PhD with that idea, and I went to a little meeting with a man named James Anderson, who was an engineer by PhD, and a person who had started to model perception and cognition using neural networks. And he and I were put up in the same motel. And this was a 2-week-long sort of summer school event at the University of Minnesota in 1975. And so I spent 2 weeks with Jim in the same motel. And, we'd walk back and forth to the venue for the meeting and so on. And I got to know something about neural networks just talking to this guy. So Jim was definitely a neural network pioneer before I was. He also was, I think one of the earliest proponents of distributed representation. So Jim had this idea of the representation of a concept as a pattern of activation over a collection of neurons. And his model was called the brain state in a box. So he had this idea that each neuron has a maximum and a minimum activation. In his models, they were usually plus and minus 1. And the box was plus or minus 1, right? But if there's 100 neurons, it's a 100-dimensional box. If there's only 2, there's a 2-dimensional box that you can see. But he sort of intuitively explained this by saying, okay, well, you put some input in, it's going to go until it hits a wall, and then it's going to move along the edge and end up in a corner. So you're going to end up in a state that represents a category from this continuous activation process. It's just like that's the way it works. You know, we have categorical perception of speech sounds, which he was studying using this mechanism. And I'm like, yeah, that makes sense to me. You know, a bunch of neurons all interacting with each other. So I just, I started thinking in terms of neural networks at that point, and that's how I got into the field.
And did you come primarily a background of biology and psychology, trying to merge the two?
As an undergraduate, I went to college wanting to major, to be a psychiatrist. You know, I had a pretty good math background as a high school student. But the things that really kind of were burning in my mind was why I found it so difficult to find a person in life to pair up with. And finding a girlfriend was always a challenge for me in high school, for example. And I, like, what's going on there and how can I understand this better? So it was mostly self-analysis that I was interested in. And I got to college and I volunteered actually to find out more about psychiatry by volunteering in a clinical setting. I had an experience that convinced me that at least that particular kind of clinical experience was not what I was looking for. So, you know, I was kind of lost for a year or two, but then I took Psych 1 and I started hearing about the people's susceptibility to environmental influences. Like, oh, you know, you could participate in a lynching if you happen to be hanging out with the wrong people. You got swept up in this crowd and you know, suddenly you'd be thinking this was the right thing to be doing. And I'm like, wow, you know, you know, people's behavior is something we should try to understand scientifically rather than thinking of ourselves as rational beings who, you know, or moral beings who are either good or bad or something like that. So psychology is really where my heart has always been. But you know, I always felt that the neural grounding made it sort of mechanistically concrete for me in a way that I found important. And I do seem to have a certain kind of mathematical inclination, even though I don't have any degrees in mathematics. But so I took a little bit of math as an undergraduate, but mostly I had to learn it after I had. So actually, during the fall of 1976, I took a 1/4 sabbatical and I studied linear algebra and differential equations so that I could understand Jim Anderson's model, because he was using, you know, linear algebra and differential equations. It's like, okay, I better understand this stuff. So I bought the textbooks for the engineering classes for sophomores and read them in my mini sabbatical.
Okay. Let's move on after you graduated. What are your most significant accomplishments, do you feel?
Well, I think my single most significant accomplishment was teaming up with the amazing collaborators I've had in my life. And I'll mention my wife first. She keeps me grounded in the real world and explains the strange behavior of other people to me in ways that deal with that aspect of what I was mentioning before in helpful ways. But also, scientifically, getting together with Rumelhart and having the opportunity to learn from him, Jeff Hinton, Jim Anderson, who I already mentioned, and Steve Grossberg, whose work was very influential, as we started into these things. Well, I don't know whether I should take any credit for any particular accomplishments, but I guess I would mention 3 things that I've been involved in that I think have been certainly very central for me. So the first one was the interactive activation model, which we've already alluded to a little bit. And that's the idea that we exploit context when we interpret any aspect of input that we're receiving. So, I mean, I don't distinguish between, there's all these elements coming our way. We focus on some of them as the focus of our attention. Others are the context that we use to constrain this. Of course, we could switch which one is the context, which one is the content. But the idea that our interpretation of any bit of information is dependent on the interpretation of many, many other bits of information in a way that's often mutual. So that, you know, your ability to see any of the letters in words depends on your ability to see all the other ones. It's not like left to right. Even in speech perception, if you have an ambiguous segment that's been, if there was some phrase like "look at the eel," you'd hear this, and you wouldn't know what it might be covering. But if it was "look at the heel of the shoe," or "look at the heel of the wagon," you'd hear "heel of the shoe" or "wheel of the wagon." So the context can come afterwards and still constrain your perception within a limited window, of course. So there's this mutual, you know, what you've heard before and what you're about to hear and what you're hearing now all work together to constrain the perception. And in the perception of letters and words, you've got all 4 of the letters mutually constraining each other by way of your knowledge about the words. So letters activate possible words, the words feed back and activate alternative letters in this interactive activation process. And I think that the brain is massively recurrently connected. There are bidirectional connections everywhere. It's like one of the first laws of connectivity of the brain. And where there aren't bidirectional connections, there's loops, that trisynaptic loops and various things like that, you know. And people are forever trying to analyze these things and sort of like this and then that and then the other thing. That's a sort of, even if it's cascaded, it's still sort of like a one directional flow. And I for me, the idea that we exploit mutual constraint satisfaction is a very central one. And it was the central idea of the interactive activation work. And again, I want to just say that although I'm very pleased to have been involved in that, Rumelhart was the person who articulated this interactive model of reading, in which he stated this idea in clear terms and led me to think, okay, well, I've been thinking in this feed-forward way myself, passing activation through the letter level to the word level, but what about the feedback? What about the interactivity? And that's why I teamed up with him. So that's number 1, I guess. Then number 2, the parallel distributed processing research group. It was really a truly awesome opportunity to learn from others and to, you know, let my own ideas take me wherever I wanted to go. And so we started this group in essentially December of 1981. I guess we wrote this little memo and sent it to people we wanted to invite. And the group was Jeff Hinton, who was a postdoc at UCSD at the time, Francis Crick, who heard about it from Jeff, Paul Smolensky, who was also a postdoc at UCSD at the time, and with training in physics. And Michael Jordan, who was a graduate student, a couple of other people, David Zipser as well, who was the person who knew maybe the most neuroscience after Francis Crick, I guess. So we would meet in this little room at UCSD, and we'd talk about neural networks. During the course of 6 months, we sort of laid out the outline for the PDP books. And so basically, it was just this effort to articulate how it might be useful to think about cognition as arising from the interactions of many, many neuron-like units, all interacting with each other via excitatory and inhibitory connections. And then the hard part was like, how do they learn, right? How do we teach these things anything interesting? And I was not, of course, involved in the breakthrough of inventing backpropagation. Rumelhart, I had gone to Boston with my wife to be with her there while she did a fellowship, and also to learn from others a year after that 6 months when we were all together. And Rumelhart, Hinton, and a mathematics PhD student named Ron Williams sort of got together and developed the backprop algorithm while I was in Boston. But I got a chance to apply it, myself, and to develop models of learning. Learning with Rumelhart, we developed a model of learning the past tense of English. With Mark Seidenberg, we developed a model of learning spelling sound correspondences, also inspired a bit by Terry Sinofsky's work, or done around the same time as that, sort of mutual inspiration between that and the past tense model. And I guess the nub of this is, and this is where I think the seminal contribution lies. And again, Rumelhart really deserves a lot of credit for this, but it's to ask the question, can we understand lawful behavior without imagining that the system is got a little man in its head looking at a list of rules and saying, oh, the rule says that I should orbit around the sun according to an elliptical orbit, so I guess I better do that, right? This is one way of thinking about rule following, but that's not what planets do. They don't read, they don't have a little man in their head. They're orbiting the sun according to these laws of physics, right? So we want to understand how behavior could be lawful without explicitly following the rules, right? And that's what all of that work was about. It was about articulating this alternative to the idea that we had to think that a cognitive system exhibited lawful behavior because it was explicitly following rules. And this created a huge backlash, all right? So I don't know if you're aware of it, but I was subjected to really fierce abuse by linguists and psycholinguists at MIT for being a proponent of this view. So Rumelhart and I had a paper on the past tenses of English verbs. And this was very titillating to these linguists, but they insisted that, it couldn't possibly be right. And there were all kinds of fatal flaws in this work. And, I think that idea is, while I was sitting there being subjected to this abuse, that instead of just having one person comment on my paper, as they usually did in their seminars there, they decided that two people had to comment because this was so fatally flawed. that they had to hear from two folks before they heard from me, right? So each of them spoke for over an hour in what was supposed to be an hour and 50-minute, session, and I didn't have much time at the end. But I was sitting there listening to all of this and saying, well, this must be important if these guys are so bent out of shape about it, I highlight it because it sits at the heart of contemporary debates in machine learning and artificial intelligence, right? So we have these systems like GPT-3 that learn language through exposure to a corpus of language. They're simply using a stream of text to make predictions for the next word that's coming along based on what's come before. So it's, in some senses, strictly left to right. I've said, oh, well, we should have a slightly larger window, to the right-hand edge, but that's a small detail really in this context. There's no rules anywhere in these systems about language, having sentences with subjects and verbs and, a sentence consisting of a noun phrase plus a verb phrase or whatever, those rules do not exist anywhere, but these models are sensitive to the structure of sentences in ways that are, quite remarkable. And they exhibit many other amazing capabilities as well, without building in any explicit rules into these systems. Now, there are criticisms of them. They're not perfect models by any stretch of the imagination, but they have begun to, I think, erode some of the long-standing commitment to building in explicit structure that many people in the field of linguistics have felt was, the only game in town, and which was why I think they so fiercely kind of rejected the ideas when they were first introduced. But I'm really proud to have been associated with those ideas. The third thing I'd like to mention here under accomplishments is what I'll call the complementary learning systems theory. And so this is work that I did inspired mostly by a man named Bruce McNaughton, who is a real neuroscientist, if there ever was one. But like me, he wants to sort of like really understand the mechanistic basis of something like memory and learning. And he got his PhD at Dalhousie University, which was where Donald Hebb had gone in his sort of retirement after leaving McGill, and was arguably the first to demonstrate that Hebbian-like learning occurred at synapses in the hippocampus. People argue about whether his experiments were really definitive or not, but they were certainly testing implications of Hebb's ideas and demonstrated consistency with those ideas. And I heard McNaughton speak in 89 or 90 or something like that about what he called the Hebb-Marr theory of learning and memory. And it like just blew me away. And essentially the Hebb-Marr theory says that learning is a matter of synaptic modification, and that memory requires a special system that allows you to learn new things quickly that complements the rest of the brain, which is a slower learning system. So Marr had 3 amazing papers around late 69 to 71. One was called a theory of the cerebellum, one was a theory of the neocortex, and the third one was the theory of archicortex or hippocampus. And And basically, he thought that the cerebellum and the archicortex both function differently from the neocortex. He thought the neocortex extracted categories and the hippocampus learned examples and learned them in one shot, essentially. Now, he stepped away from that work, even though I think many people nowadays think it was seminal. He stepped away from it and started doing vision, stopped worrying, and started arguing against being inspired by the brain. And instead, you had to think about the computational problem the brain was solving, which was an important contribution as well. And I don't want to knock that, but he introduced this idea, and he himself was inspired by the fact that, in humans and animals, if you remove the archicortex, the medial temporal lobe on both sides of the brain, as Scoville did in his very famous surgery on patient HM in the early 50s, you create a system that knows all of its encyclopedic knowledge of the world. It can talk to you. This person, sounds like an ordinary human being and can greet you and say hello and introduce himself to you if he's never met you before and carry on a conversation about various things. But, if you step out of the room for 2 minutes and come back in, he'll look at you like he's never seen you before and he'll introduce himself to you again. So he can't learn new things, but he certainly learned a lot in his life. He learned how to speak his native language. He learned how to understand and engage in conversation and make appropriate, So we have the ability to learn in ultimately store knowledge in these parts of our brain. But the ability to learn new things quickly depends crucially on this other system. And I think that, cognitive psychology, the effort to understand human memory wasn't, really cognizant of that appropriately until the cognitive neuropsychologists were doing their own thing. They didn't really, John Anderson, a different Anderson, the leading theorist of human memory in the 70s and 80s, is not referring to this work at all. So I started thinking in terms of, really understanding how it is that we can learn from the point of view of complementary learning systems. And I find it important, for me at least, in that it bridges the effort to understand developments, gradual learning over a lifetime of experience, with an effort to understanding learning systems in the brain and how they're organized. So the hippocampus, of course, is very important. It's crucial for learning new things quickly, but you can have a profound hippocampal lesion and gradually develop a fairly normal. So similar to HM, there were patients who were born without a very important part of their medial temporal lobe. It was completely destroyed due to hypoxic incidents around in early life, at or around birth. Sometimes it's hard to know exactly when these incidents occurred, but the part of the hippocampus is completely destroyed, and the person is incapable of learning arbitrary new things in one presentation. But he ended up being able to go to school and become, reasonably well educated. Interestingly, so anyway, there's this developmental side and this cognitive neuroscience side, and they come together in a way that I find exciting in the complementary learning systems. I think that'll be the end of my answer to your second question.
Okay. Actually, going off a little bit on a tangent, since Dave Rumelhart is no longer available to be interviewed, could you maybe say in a few minutes something more about your general summation of what he accomplished?
Well, I think, I think Rumelhart was, in a sense, the prime mover of two of the three things that I've talked about, in addition to being the prime mover of the introduction of the backpropagation learning algorithm. And so his paper on interactive models of reading that, I think he wrote in '76, that appeared in a volume a year or two later, but started him down this path of wanting an alternative to conventional, good old-fashioned AI type models, which he had been working with in the early '70s. And I think he read a piece of work by a woman named Joan Bybee about language, about making past tenses, as a matter of fact. And it got him thinking about this idea about not needing to build in the rules. And so he really was the prime mover there as well. Joan Bybee was arguing, look, these, you can't, rules aren't the right way to understand some of these phenomena, but she offered, appeals to alternative ideas like analogies or something like prototypes, but it was, verbal kind of characterization, and Rumelhart really wanted to cash that out in the model. And then, just thinking about the kinds of things that you can do easily in symbolic computation. And he couldn't get a neural network with the learning algorithms that existed at the time to do it all, namely negation, right? You couldn't negate a proposition in a neural network. And it's like, okay, we got to fix that one, right? So he developed backprop essentially to solve the negation problem. And, XOR, you could think of XOR as being like a mini example of a negation problem. You have one element. If it's on, you want the output to be on. If it's off, you want the output to be off, unless the negation bit is on. If the negation bit is on, you flip the meaning of the first bit. Right? That's XOR. And Rumelhart's initial instantiation is you have these two units, and this one other one over here. And they talk directly to the output as you could in a simple associator, right? Where you're training it with the perceptron convergence rule. But you got this unit, this hidden unit off to the side, which, you want to recruit that unit to help you in case you need to do something with the combination of the inputs. That was the way he thought about it at first. And so how do I get a teaching signal to tell that unit to train its incoming connection weights to allow me to negate elements of the input? And he wasn't going to stop thinking about this problem until he came up with a solution. So my friend Gary Cottrell at UCSD describes Rumelhart as, okay, think about a great big steamroller. And now think about a small little rock, that's sitting on a concrete slab somewhere. Well, this rock looks pretty tough, but Rumelhart's the steamroller. And that rock just ain't going to have a chance. Rumelhart is just going to run right over the damn thing and crush it, So that was Gary's analogy to Rumelhart's sort of like tendency to persevere to find the solution to a problem that he wanted to solve. And I always liked that. He was a bit shy until you got to know him, in which case he wasn't shy at all. Some of us heard his innermost thoughts escape from his mouth from time to time. And, you know, we all have innermost thoughts, I think, that we probably don't want to let escape. But once you got to know him, he was very open. And yeah. So, and he was driven to solve the problem that he saw that needed to be solved, and sort of offer his alternative perspective.
Jane, how about now? What are you working on now?
Yeah, so I'm working on mathematical cognition. Or we might think of it as the ability to exploit culturally invented formal tools of thought. So what is mathematics? Mathematics is a set of culturally invented formal tools of thought. That's how I define mathematics. I'm not unique in this respect. I define it that way. I think there's a man named Hirsch, who was a mathematician, maybe still is on the faculty at Berkeley, who introduced that way of defining what mathematics is. And there's another man named Saunders McClelland, also at Berkeley, who has similar ideas. So these are systems that humans invent to make it possible to think rigorously. And they require the development of, refined ideas and successive sort of honing of these formal systems. So people invented explicit counting systems only if their cultures needed them. Okay, there's still cultures, very few, maybe not still today even, but there were, like 10 years ago at least, still cultures where people completely eschewed the idea that it was useful to learn how to count. They didn't need it in their culture. They didn't want anything to do with the world of the Brazilian Spanish, like, leave us alone. We're happy here in the jungle. We will take some batteries next time you come back, but it's about it, right? They don't want to be a part of that world. And they don't need number. They don't have that system, and they are happy without it. But of course, when people start settling and raising crops and storing crops over the winter, they need to keep track of the volume and quantity of their crops that they're storing in somebody else's barn and so on. And then they start inventing systems for representing exact amounts. And these systems, gradually became more and more refined. But even in the times of the Greeks and the Romans, where we had quite sophisticated mathematical ideas, they're working with these non-place value systems, right? Like the Roman numeral 10 is just an X, and things like that. It's so what do you do when you get to 10,000? Well, you have to invent another symbol or something like that, right? And so also Euclid's geometry is actually flawed, and there are gaps in his theorems, things he claimed he had proven that he hadn't really proven, and people reformulated these ideas. And so these systems were invented by humans to allow us to extend our mental abilities. And the advanced capabilities that we have, that Rumelhart had, I guess, are things that come to us as a virtue of our being immersed in cultures which have invented and perfected these tools. And he was amazing at picking up a new one. He would just go like borrow the book from the library. You know, it didn't take him a whole quarter to learn differential equations. This is what I have chosen to think about. And when I think about it, I'm very inspired by a statement I found on a park bench that's due to the mathematician Poincaré. He actually was an engineer, physicist, mathematician. He thought a lot about physics and things related to relativity and so on, slightly before Einstein was thinking about these things. He said that it is by logic that we prove, but by intuition that we discover. And my goal is to understand how neural network like systems that are very good at like gradually integrating knowledge over, developmental time, gradually acquire intuitive abilities to have insights that then we can use these formal tools to prove. But it's more circular than that. You sort of like you actually develop the intuition in the context of the tool, and so it's really mutual constraint satisfaction. It's not like they have these completely complementary roles. They interact with each other more than that. That's what I'm working on now.
Okay. Going back in time a little bit here, what about the early days of AI, the early days of the International Neural Network Society? What are your recollections there?
Well, to be honest, I'm a little fuzzy on some of that. I always, as I've said, primarily identified as a psychologist, and I didn't find myself going to meetings that were specifically neural network oriented meetings all that often. I went to some, but I sort of thought of myself as like, I wanted to go to the Cognitive Science Society meeting every year. I still do that. I remember there was a nice symposium at the Cognitive Science Society meeting in Amherst. It met in Amherst, and Andy Bartow was there, probably Sutton was also there at the time. So people who were around in the early days of neural networks. I also have memories of interactions with Steve Grossberg, who, I haven't mentioned too much so far, but when Rumelhart and I were developing the interactive activation model, there was one paper of Grossberg's that was extremely important to us in getting our networks to behave properly. We read it, we cited it in our paper. I think Steve felt that we hadn't recognized the full extent to which he'd already anticipated many of the ideas in our paper. And I think, William James also anticipated several of these ideas. So I certainly think credit, should be widely disseminated for all of these kinds of things. But Grossberg really knew what the hell he was talking about when it came to the fixed points of various dynamical systems. And that was the mathematics that we needed to get our neural networks to stabilize in the interactive activation model. And you know, he's right in the sense that he was concerned about this notion of bidirectional interaction, and sort of settling into a state where there was some sort of unit that represented a synthesis of a whole bunch of elements, and they mutually exciting each other in this bidirectional way. I do remember I went to an early INNS meeting, but I wasn't part of the core of that community so much at that time. And I also went to an early, what was then called NIPS, now NeurIPS, and also wasn't part of that community either. I didn't understand all the math that those guys were talking to each other in, and I found myself not, you know, being able to engage in conversations with people at those meetings. So I sort of withdrew into my psychology a little bit during that period. I realized some years later that this withdrawal was not useful to me, and I no longer withdraw, but I still you know, have limited bandwidth. I can't go to every meeting. Yeah.
For the future of societies such as INNS, what do you think that the society's role can be useful?
Well, I think that you know, bringing people together, sharing ideas across boundaries is essential. You know, it's how science progresses. And you know, when I've been involved in things like creating the Center for the Neural Basis of Cognition at the University of Pittsburgh, and jointly with, I was at Carnegie Mellon, but it was joint with the University of Pittsburgh, or when I came to Stanford, the Center for Mind, Brain, and Computation. You know, it's all about the idea that people coming from different perspectives bring different ideas that are going to turn out to be useful as constraints, and where we should be listening to each other in this mutual constraint satisfaction kind of way. So what I look for in scientific meetings is opportunities to exchange ideas with other people. You know, journals are useful for this purpose as well. And I feel like, you know, I'm definitely not a huge fan of rapacious sort of profit-oriented publishing companies that, you know, hire people whose primary goal is to enhance the profit-making potential of the corporation. And so I always think, okay, well, when the journal, when the society is in control of the journal, then that's much better. You know, I think Science Magazine is a little bit too much competing with, you know, Nature and Elsevier, Springer Nature and Elsevier in that regard. But so I think that societies like the INNS, you know, to the extent that they have publications that are motivated by disseminating ideas rather than enhancing the profit of the corporation, are really important and valuable, and bringing people together in scientific meetings and helping them share ideas with each other. Those are the things I think INNS can do, and other societies can also try to do.
A general view of the way AI research is going on at the present time. What do you think people are doing right or wrong in AI now?
Well, they're certainly investing a lot of resources, which is exciting, and they're attracting some of the very best minds. So when I think of I think these questions have attracted some of the very best minds, since Steve Grossberg and Jim Anderson were attracted to these ideas in the 60s and 70s, and maybe Rosenblatt is another one, right? I mean, he was way ahead of his time, that guy. I haven't mentioned him, but he wrote a really, really beautiful book laying out his perspective in the 50s. And he was ahead of his time because the computing wasn't there to actually, there weren't enough cycles to see what the implications of his ideas were. And it's something we haven't commented on very much, but even for Rumelhart, for example, with backprop, he wrote the program, he started it running, he came back the next morning, it hadn't converged, he thought it wasn't going to work, so he worked on something else for a couple of years till he got a faster workstation. And he tried it again on the faster workstation, and lo and behold, it converged in half an hour, right? Nowadays, it converges in under a second because we have so many more cycles. So that little XOR network that I was mentioning before, it didn't converge the first time he tried it. But it was really, he just had the wrong expectations about how many cycles it would take. Obviously, of course, it does take a certain amount of experimentation and fine tuning and, rethinking and introducing new ideas and so on to get these things to work. But when in between 83 and 86, when, the workstations were actually fast enough and these things did start to work, that was, so the paper wasn't published till 86, but I think he first had the code that was essentially implementing the idea in like 83. So the cycles are very important for this sort of stuff. And, well, OpenAI decided they had to sell themselves to a profit-making corporation to have enough capital to buy enough cycles to train GPT-3, right? And so that's one of the things that they're doing, is they're investing in all these cycles. And Google bought DeepMind and gave DeepMind all the cycles it needed to be able to solve Go and other games like that. So one thing that's led to progress is all of these cycles. I don't know whether people are doing the right or the wrong thing, but they're definitely using a lot of cycles. And also, they do have some of the very best minds at all these places. I have this amazing privilege of having a part-time consulting position at DeepMind, and I benefit immensely from the opportunity to share ideas with these people. Well, what I think people are doing wrong, I think we have to explore many paths. I guess, I'm not a fan of proprietary research. I think that's that's the place where I would make a comment. If there's proprietary research still going on in AI, I think that's a bad thing. I think OpenAI was a good idea to help encourage openness. I'm a believer in the academic model of like open sharing of ideas, but the world of putting your paper out on archive and having public comment on it is a super important part of what is right about what's going on these days, and more of that.
What advice would you give for a researcher just starting out in the field?
Wow, it's such a that's a hard question. It's with so many people now flooding into it, you know, OpenAI, Google Research, Google Brain, DeepMind, Facebook AI research. We could go on and on. The Vector Institute in Canada, the other institutes, the Mila Institute, other places like that that are really investing heavily in this field. It's a very challenging time imagine that you could find your own niche and somehow make an impact. And what would I say to a young researcher? Well, I guess the only thing that ever worked for me was to like follow my instinct. So I will tell you this story, okay? When I was a first-year graduate student, I worked very closely with a professor on my first-year research project. At the end of that project, I found myself feeling like I didn't want to continue in that particular direction. And I teamed up with another PhD student who had actually studied cognitive psychology with the man who wrote that phrase, physiology is only of peripheral interest. Now, his name was Ulrich Neisser, and he wrote a book called Cognitive Psychology that was published in 1967. And he taught that, and he was at Cornell, and Jim took his classes, and so he was inculcated in these views, and he came to Penn, where I was a graduate student, and I learned from Jim about Neisser's ideas, also reading Neisser's book, but you know, with somebody who I could talk to about it as well. And but the story I want to tell you is this, just context for this, is that Jim's sort of overriding feeling was that he felt like he had come along a bit too late. And all the great ideas had already been had. And, you know, Neisser had written a book, and he reviewed many, many interesting pieces of work that had already been done, that's for sure. There was lots of cool things that people had done in the relevant literature that Neisser reviewed in his book. But it just wasn't true that all the good. I mean, clearly there's still a huge amount left to do. And I guess I would say that you shouldn't think that you're too late. That's one thing. And the other thing is that, you know, you should always follow what, you know, you see a gap, you see where people are not working on a problem that you think they ought to be working on. You know, in my case, it was the idea that processing was continuous and cascaded, and that was in contrast to the prevailing very discrete, stepwise kind of computer metaphor way of thinking at the time. And that led me into these ideas. Rumelhart, you know, was thinking in terms of interactivity and, you know, and then solving that negation learning problem. So, you know, finding that opening where the field isn't going. Of course, I don't have a recipe for finding it, but if you feel like you're noticing something, go in that direction. Think about that.
Well, Jay, thank you very, very much. I've much enjoyed your interview, and we'll talk later at some point. So thank you very much.
You're very welcome.